Hi everyone, welcome to the lecture, the fourth interaction session for the course on advanced robotics. My name is Soumya and I'm PMRF fellow at IIT Gandhinagar. So today we'll be talking about a couple of things which would start from Jacobian and then we'll move to singularity. Then we'll also see what is redundancy. So I hope all of you have already gone through the lectures, but still we'll have some recap, some problem solving, and a MATLAB question. So I hope by now you're familiar with MATLAB. We already had MATLAB session in the last to last class. And I think knowing MATLAB would be good. You should be able to know how do you find out the Jacobian there, if there is some function available. So all these things would really help you. I encourage you to start with MATLAB. I hope everyone uses MATLAB. If you don't have the licensed version of it and you're not able to use it on your system, there is MATLAB online, which is already available. Please go through it and practice the problems that I'm telling you. Even when I'm solving the MATLAB problem in the class, then also parallelly you can solve it there. It will help you get hands-on with the coding, with the syntax that is being followed, how are the matrix operations done, and there there is a alternative of MATLAB. I'm not remembering at this moment. It is something with O. If anyone remembers, you can tell me. Uh, just a second, I'll check and tell you. It has very similar syntax to that of MATLAB. A Scilab is one of the things that you can use. Yeah, Octave. So you can use Octave. The syntax is pretty similar and you can practice and it is available like free. It is open source software. So you can use it also to practice MATLAB questions. So anything that you are doing, so in this course basically you are dealing with the things that are mostly theoretical and then you apply it with a problem. But how do you get it from the code? How do you solve the forward and inverse kinematics from the code? And then how can you find out what is a Jacobian? Next we'll see much more things later on. We have biped and grasping thing also coming on. So there also we'll have the MATLAB problems. So get familiar with the environment. Get to know how matrix is defined, how it is operated, and what is Sims toolbox, what are the tools available that we can use to like calculate various things. There is something called Simulink in MATLAB. Are you familiar with it? Like Simulink has kind of all the, for example, you have the GUI kind of interface. It's not like you have various blocks for simulation. So if there is a gain, you get a gain. You can always have a tan calculator. Then you can have the motors directly. You don't need to define what are the kinematics and dynamics of the motor and then you calculate anything. So we won't be like, you won't have to go into those. There will be always a motor available there. You can directly take a DC motor from there, provided the inputs. You can use it for control. You can directly define the PID controller. So Simulink helps in that. So either you go with the code which gets stored in this .m file, or you go with Simulink which gets stored as a .slx file, and please try to practice them. They will really be helpful in whatever work you do. If you are from electrical department, I think you might be doing this for power system. If you are from mechanical, then you might do with various machines. So yeah, I know of all the motors that are available there. You have BLDC and everything, and I think it would be great if you learn all those things. I am doing whatever is required for this course. So yeah, I'm taking some MATLAB problems, but yeah, you have to practice or you know it would be really good for you. Okay. Now, before starting with the thing, I think Sanjana has asked that theta is the link angle, but in assignment it is marked wrong answer. May I know the right answer? I think I'll write it here. So of all the things that we had learned in DH parameter, A was the link length, right? Alpha was link twist. D was link offset. This was joint angle, right? I don't know if you have somehow understood this to be link angle. Not sure about it. If you say link angle, it could go more similar to link twist. I don't know what are the options there. So if you can tell me what is exactly the question, then I'll be able to help you. I don't have it opened with me right now. But yeah, this is the joint angle because this is essentially the angle between all the joints. So that is why when we have a revolute joint and let's say it can rotate by theta 1, then we say that yeah, theta 1 is my joint angle and it can be used for like calculating the homogeneous transformation matrices by calculating all the angles theta 1, theta 2, theta 3, as many number of revolute joints you have. All right. And then this is yeah, so I hope I'm clear with this. Okay, we'll start today's session. Before we start, can anyone tell me what you understand, what you understood by Jacobian?
Excuse me, ma'am.
Yeah, say.
Ma'am, the question was the parameter in the assignment question which Sanjana ma'am has told is the parameter in the DH table for the link angle is. That was the question, ma'am.
Okay, for the link
And,
angle.
and the options were theta, A, alpha, and D.
Okay, so I think this
And
angle. Yeah, continue.
ma'am, what will be the answer for that question?
I think it should be link twist. So if this link,
There they have given the answer as alpha.
yeah, that's what I'm saying. Link angle should
Uh,
come mostly with link twist.
okay.
Okay, because that is basically the angle between z axis. So it is not close to joint angle because the joint angle, how do I say, link angle is basically the angle you are getting between the links along the z axis, in between the z axis. So I think it
Okay.
should be alpha and not theta. Okay. Okay. Before we proceed, I hope all of you have gone through the lectures and I really want to know what did you understand from Jacobian? I mean, this is going to be the first question in our solving the problem which will be solving. So, can you tell me what did you understand by Jacobian? Or why do we need a Jacobian? Or why did actually Jacobian come into existence?
Ma'am, by definition wise, we can say that it relates the interfactor velocity with the joint velocity.
Right, very good. So, Jacobian is basically calculated by getting the partial derivatives. So if you have a function, just a second. Yeah. Let's say you have some function, something of sort, let's say y, and it depends on f of x1, x2, x3, and so on. Okay. For simplicity, I'll consider it to be x1 and x2. Let's say it depends on these parameters, all right? So if it is a function of x1 and x2, and then I want to take the derivative for some very incremental change, for some incremental change only, not a very big change. So if something is related to incremental change, it's definite that we are going to differentiate it with respect to some variable. So let's say, so if we try to find out what would be a small change in y, it is going to be partial derivative with respect to the first variable, okay, plus with respect to the second variable del x2. So this is the way in which we define the partial derivative. From here only Jacobian comes into play. All right. As Bindu said, that we want to, Jacobian is basically used to find a relation or relate end effector velocities to the joint velocity. So let's say you have a 2R manipulator. Okay. This is your 2R manipulator. Let's say this is your end effector and it has some, you want it to reach some x and y position. Then you had the angle, this is theta 1 and this is theta 2. All right, these two are the angles. Okay, should not be this way. Okay, these two are the angles. So in the last class we saw that we use forward kinematics and inverse kinematics. So let's say given unknown. In forward kinematics, we are already given with thetas and then we want to find out what is x and y. In inverse kinematics, we are given xy and then we want to find out what are the thetas. So this is what that happens with kinematics, inverse and forward kinematics, right? But let's say we want a relation between velocity. So if I want some relation between uh, x dot and y dot with theta 1 dot and theta 2 dot, I want my end effector to follow a particular velocity trajectory. I want it to go from this place to another place with, let's say, 2 meters per second. So I want the end effector to move with a certain velocity and reach a position. But how would that translate to the joint velocities? So if you're supposed to find some relation between theta, so you already have some relation between x and theta, right? We have already seen this, that you have x is equal to the first link. So if it is L1 and if it is L2, it is L1 cos theta 1 plus L2 cos theta 1 plus theta 2, right? This is your x. Okay. Similarly, for y, you will have in terms of sine. So you already have this. But now I want to find a relation between the velocities. So I'm definitely going to differentiate this. Now the differentiation should happen in such a way that we get how x depends on the incremental change in theta 1 and incremental change in theta 2. So things have to go in the way that we are able to establish a relation between all of them, and then it is definitely done by partial differentiation. All right. So I think for 2R manipulator, just I want to reiterate the things that we have done. So, okay. Let's say here is my link and then this is my manipulator. This is my x, y. This is theta 1 and this is theta 2. Alright. You have already seen the DH table and everything, and from there you already know this, that x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Y is equal to L2 sine theta 1 plus L2 sine theta 1 plus theta 2. Alright. Now we want to find a relation between x dot y dot and theta 1 theta 2 dot. Alright. So for that we'll differentiate. So let's say I write dx and dy here. And here I want to find a matrix and then I have d theta 1 and d theta 2. Alright. So if you differentiate the first term with respect to, I'll change the color. Let's say we want to differentiate the first term with respect to theta 1 and then the second term with respect to theta 1. So it would come here. When we differentiate this x with respect to theta 2, it would come here. Similarly, y with respect to theta 1 would come here, y with respect to theta 2 would come here. Okay. So let's fill this. So let's say you take the first, or I'll write it. We want to do del x upon del theta 1, del x upon del theta 2, del y upon del theta 1 and del y upon del theta 2. Alright. After this, if you try to find this out, what will you get? It would be cos theta 1 with respect to theta 1 we want to differentiate. So it is going to be minus sin theta 1, right? So it is minus L1. I will now use this convention. Minus L2 cos theta 1 plus theta 2 with respect to theta 1 is minus sin theta 1 plus theta 2. So I'll write it 1, 2. Okay. Similarly, when you differentiate x with respect to theta 2, the differentiation for first term is going to be 0 and for the second term it is going to be minus L2, it is going to be sine 1, 2. Okay. Similarly, here you will get L1 cos 1 plus L2 cos of theta 1 plus theta 2. Okay. The last term with respect to the differentiation with respect to theta 2 would give you cos L2 cos 1, 2, theta 1 plus theta 2. So you get a Jacobian matrix of 2 cross 2 order. Later we'll see that or you have already gone through the lecture, right? So the Jacobian won't always be a square matrix. If it is not a square matrix, okay, why do we actually need it to be square matrix? That we'll see in just a couple of minutes. But yeah, so and from here you understand this also, right? That dx and d theta are all incremental. Okay, for a very small change we are seeing this. Okay, now so from here what do you get? We establish a relation that x dot is equal to j into theta dot. Don't take x and theta to be just one value. It's not just one value, it is rather a vector. So you can see from here, this x comprises of dx and dy and theta comprises of d theta and d theta 2, d theta 1 and theta 2. All right. Okay. So we get to know that J relates the end effector velocity to joint velocity. So this is your end effector velocity and here is your joint velocity. Okay, I hope this makes sense. Now, so this when I said this is because I have calculated in such a way that given theta dot, if you want to find out x dot, you will pre-multiply theta dot with a Jacobian matrix, all right? But if we want to find out theta dot, then what we'll do? We'll take the inverse of Jacobian. And why do we do that? So I'll write it in this way. Let's say I write J inverse x dot. It would be J inverse J into theta dot. From here you can write J inverse x dot is equal to identity matrix into theta dot. This means theta dot is equal to J inverse x dot. So this is really an important relation. Now, since we are taking an inverse, this becomes really important because when you are taking an inverse of a matrix, first of all, Do you know any way in which you can take the inverse of non-square matrix? Any idea? How do we do that? Okay, just let me reiterate my point. So in this case, it was a 2 cross 2 matrix, right? And we we know how to take the inverse of 2 cross 2 matrix, right? For a square matrix, it is going to be some row reduction type of thing where you convert it into uh, convert it into some simple form and then you take the inverse, or the other thing is you calculate the adjoint and then divide it by the determinant and you take the inverse. Okay, but determinant calculation for non-square matrix is not possible. So in that case, how will you take the inverse of this matrix? So you have a method to calculate the inverse, and that method is pseudo inverse. And it is very simple. Uh, I think you have a command for this in MATLAB as well. In Python, I remember, we can directly take the pseudo inverse. You don't have to write the full formula for pseudo inverse, but you can just uh, use the command. Just a second, I'll check. Yeah, yeah. So it is Murray-Penrose pseudo inverse, right? So we can directly this function PINV actually helps you take the pseudo inverse. All right. So let's say we want to take we have some metrics defined over here in MATLAB. You know the way of defining, right? There is a row, then it is separated by a semicolon, then there is another row, then it is again separated, and then there is another row. So this is the way in which we define the matrix. When you want to take the pseudo inverse, let's say I say B is the pseudo inverse, I'll just write PINV of A. So B will actually be pseudo inverse. Okay, I hope this makes sense. In MATLAB. In Python, if you have A matrix and then you want to find out the pseudo inverse, you are going to use NumPy library. I hope you are familiar. If you're familiar with Python, you will know NumPy library. And inside NumPy library, we have something called linear algebra to which we can subscribe. So this is linear algebra. So we write np dot linear algebra dot PINV of A. So this helps you calculate the pseudo inverse in Python. All right. I hope this is clear. So these are really useful. You will have anywhere, any robotics thing that you are going to use this only. So this would be really helpful for you. If you want, you can note down the commands also. Okay. So we can take the pseudo inverse, but obviously if you write theta dot is equal to J inverse x dot, that means theta dot is equal to J inverse is calculated by adjoint of J upon determinant of J, or I would not write it in this way, I'll just write it determinant of J into x dot. Now what if the determinant becomes 0? What will you do? If the determinant becomes 0, what would happen? My theta dot, if my determinant tends to 0, my joint velocities would tend to infinity, which we cannot achieve. Our motors cannot achieve infinite velocities, right? You cannot have infinite RPM of a motor. So this is not possible. So there are conditions in which we may reach this stage, and that could be a problem for us. Okay? So this is known as singularity. Okay? So there are two types of singularity. You have already read this, right? It is boundary singularity. And what is meant by boundary singularity? For 2-hour manipulator, you have seen, right? If you stretch your hand completely, and let's say your shoulder joint is fixed because you have a 2-hour manipulator. If your shoulder joint is fixed and you stretch your hand completely, you won't be able to take it back. You'll basically lose 1 degree of freedom that allows you to move in this direction. You'll only be able to move your fist left and right, but you won't be able to take it back and take it forward. That is a max stretch you have, and you cannot even pull it back. All right. So that is the condition with boundary singularity. And for some cases, it does not happen in 2-hour manipulator, but in other robots, you can have boundary interior singularity. Okay. Okay. So we'll have the question later also, but I want to take this up now only because we'll be dealing with a couple of questions which will be based on 2-hour manipulator only. So let's see how we should do. Okay. So for this 2-hour manipulator, this is my end effector. Okay. I have already calculated what is the Jacobian, right? This is the Jacobian for 2-hour manipulator. Now, if this is the Jacobian, if I want to find out, if let's say I am given theta dot j x j inverse, right? If I want to find out what is the, let's say you are given this, that what is the end effector velocity we desire. Okay, so if you are given this, and then we have to calculate this just to find out what should be the joint velocities, because that is what you are interested in, right? You want to say that you want to have an end effector velocity of 2 meters per second, but how do you achieve it? For achieving it, you need to provide some velocity to the joints, then only you'll be able to achieve it, like, right? Directly end effector किस velocity से move करेगा, you can never know. तो वो पता, to get some desired motion, you need to give some desired velocity to the joints. So calculating it is really important. So for that we need this Jacobian inverse, right? So let's say I want to find out Jacobian inverse, but I want to know if it is going to be singular at some point. So let's say I want to know singularity at what value of theta, when it is actually going to be singular. It can be theta 1, it can be theta 2. You understand by this theta dot, right? It contains both of them, theta 1 dot and theta 2 dot. So if I want to find that when it would be singular, that means what I actually want to find is theta dot is equal to adjoint of j upon determinant of j into x dot. I actually want to find out at what point of time it would reach a certain phase where this would become infinity. If this becomes infinity, means the motion is not feasible. We won't be able to reach a certain point. And when is that possible? When theta dot goes to infinity. That really means that z determinant goes to 0. So we want to find out when does determinant go to 0. So for this 2-hour manipulator, I mean you have already gone through this in the lecture, but still I want to take this. If you find the determinant of this thing, so you actually multiply both of these terms and then subtract with the multiplication of these terms. When you find a determinant, you have already seen that the determinant is L1 L2 sine theta 2, right? And theta 2 was this angle. This is my theta 2 angle. So you have found that the determinant is equal to L1 L2 sine theta 2, and for reaching singularity condition, it has to be either equal to 0, it has to be equal to 180 degree. Alright, L1 and L2 cannot be 0, right? Both of them are some finite values. So the only possibility we have is that sine theta 2 goes to 0. So let's say sine theta 2 goes to 0. Sorry. Sine theta 2. Yeah. Goes to 0. Then theta 2 is going to be 0 or 180 degree. So you can understand very well that when our configuration is of this type, where this thing is completely stretched in the workspace. Let's say this is my workspace. When it is completely stretched, you won't be able to move in this direction. You won't be able to move in this direction. You can only move in this direction. So you have lost it. It already has 2 degrees of freedom, right? But you have lost the ability to move in this direction, and now you can only move in this direction. All right. So you are not able to achieve all the motion that it could have done. Whereas if the manipulator would have just been like this, here, somewhere here in the workspace, you would have been able to move in all the directions. You would have been able to utilize theta 1 and theta 2 both to do your works. But in this case, your theta 2 goes to 0. You cannot move it anyway. You can just traverse the circle and you will be able to move along the tangents of the circle. So you have already seen ellipsoids, right? That come from singular value decomposition. We'll be coming to that, but okay. Other thing is, when it's 180 degree, what does that mean? It is here, and then you have the end effector here only. So again, you cannot move. So yeah, this brings us to singularity condition. All right. The other thing is, we'll have this in question as well. I'll take this up now only. Yeah, it was very well taken in the lecture, but still I want to emphasize that when you are given a writing task, how do you decide what should be the angle between your upper arm and lower arm so that you can write optimally and efficiently? I mean, why don't you write by stretching your complete hand and then writing at some further point? Let's say you're able to see, but why don't you write it there? Why is that not optimal? Why do you prefer writing it at a certain angle? And I am sure you know the angle. What is that angle? But still, why do you think that happens?
The energy required is high.
Yeah, for all the other configurations, the energy required is high. So there is a certain angle where you find that, okay, at this angle, I am able to optimize the energy spent. And how does that come? It comes because, so let's say for your hand, consider it to be a 2-hour manipulator only. And the determinant, okay, for that. For minimum energy, you want theta dot is equal to j inverse of x dot. Theta dot is equal to adjoint of j upon determinant of J into X dot. From here you can write, you want to minimize the energy, right? Means you want this to go minimum. You don't want to move your hands with a high velocity that you consume a lot of energy in the form of kinetic energy. We don't want to do that. We want to make our joint angles change as little as possible. All right, we want that. So if we want that, what we really do is we want to minimize this theta dot. So for minimizing theta dot, the way to do this is to increase the determinant. And my determinant was L1, L2 sine theta 2. Let's say I take this to be 1, I take this to be 1, and then sine theta 2, it should be maximized. What is the maximum value of sine theta 2? It can just go to 1. 1 is the maximum value. And when does it achieve 1? It achieves 1 at theta 2 is equal to 90 degree or 270 degree. So for 2-hour manipulator, when you have the configuration of this type, where the angle is 90 degree, or it could be, I mean, you can have this in this direction if you want, it would be 270 degrees only. So if it is 90 degree, then this is the best way in which we can write. I think I should make it more clear. This configuration. So this angle would be 90 now. And then you write. So we want to minimize energy and hence this happens. Okay. I hope all of this makes sense. After this, okay. What do you understand by redundancy? You saw redundant manipulators and then you also saw manipulation ability. So what is redundancy in manipulators?
Ma'am, if we might have many links, but one of the link will not be used. It will be inoperative.
Yeah. So the task that you are supposed to do does not need all of these links. You have far more, yeah, you have far more degrees of freedom than required. Let's say अभी काम ही यही है कि I have to stretch my hand and move it in a circular way. The other joint that I have where theta 2 is 0 becomes redundant. I don't need it to do that. Okay. So redundant manipulation, you have more degrees of freedom than required to do the task. And then I think it was covered. Then you have the concept of pseudo inverse. I told you how to find it also. The other way of calculation is you find out the J transpose, multiply it with J, and it's a formula. Okay. Apart from that, okay, I think, okay, manipulation ability. So, manipulation ability is also called manipulability. Okay, so it is basically the ability to sorry, to move in a particular direction. Okay, so in this case you are able to move in this direction only, whereas in this case you are able to move in two directions, both of these directions, here and here, all of these. Okay, so there is a very important formula that you need to take a note of, that for non-redundant manipulators, your manipulability is determinant of z, whereas for redundant manipulators, and it would mainly happen when your degrees of freedom are more and your Jacobian is not a square matrix. So for this, your uh, manipulability is determinant of J transpose. All right. So this is very important. Mark it. Okay. And why do we actually need to do this? Because if you have uh, just this, if you have a 2 cross 2 matrix, if you have a 2 cross 2 matrix, you'll be able to find out a determinant. But let's say your Jacobian is somewhat of 2 cross 6 matrix. You won't be able to find out a determinant. So you multiply it 2 cross 6 को multiply करो 6 cross 2 से and then you get 2 cross 2. Find a determinant, take the under root of this determinant. All right. That is why this is done. So this gives you the manipulability and okay. Okay, now let's proceed with the question. Okay, I hope this question is really simple for all of you. It was already answered in the beginning of the lecture. So Jacobian matrix relates what? So I think do you remember what is the how does Jacobian matrix relate force and torque? Do you remember it? Okay, I tell you, you can Google it and then say the answer. What is the relation between force and torque? How are they related? Using Jacobian. I want this answer from your side.
Torque is equal to Jacobian transpose into force.
Torque is equal to Jacobian transpose. Okay, let me write this one. X dot is equal to Jacobian times theta dot. Right. How can you remember both of these expressions together? I mean, if you take the analogy, na? So, okay, before that, I'll clarify what is force and what is torque. This is correct. Thank you for the answer. Yeah. Okay, this is force at the end effector. So let's say you apply a static force at the end effector, and this is joint torque. So a torque that is being generated by the motors placed at the joints. All right. So this is the relation. But let's say you are, so what does this mean? This means that force is equal to J torque, Jacobian into torque, right? But if you try to find an analogy between this and this, it's difficult, right? Because see, force is this is, in this case, this is related to end effector, and this is related to joint. Whereas in this case, F is equal to
Excuse me, ma'am.
huh,
Ma'am, torque is Jacobian transpose into force. Ma'am, I think you have written inverse.
that's why, yeah, transpose, right, right. So here, if you write uh, for end effector, it is going to be force, right? And then, or what I will say, torque is equal to Jacobian transpose into force. This force is associated with end effector, and this torque is associated with joint. So in both of these cases, you can see that अगर end effector का velocity is equal to Jacobian into joint velocity, it does not go with torque and force. It is the inverse relation basically. So if you are supposed to write this for force, you'll have to take an inverse. But a force will be equal to, let's say I take J transpose inverse on this side, then I'll have inverse into torque. Okay, so inverse comes into picture when we move from velocity to force. Okay, so remember it in this way, that you don't have the same relation between both of them, it's different. Okay, let's move to the next question. The joint velocity becomes infinity when the value of the determinant of the Jacobian is equal to, okay, so from here you can write theta dot is equal to J inverse x dot, and Jacobi, if we want to find out, or determinant is equal to, if the determinant is equal to 0, then to impart even a small velocity x dot very high, uh, or infinite, I would say infinite joint velocities are needed. So this happens when the determinant is equal to 0. So this is your correct answer. Okay, in this case I did not tell you the answer, right? End effector, velocity and joint velocity. Okay, let's move to the third question. Singularities are points in the workspace where the determinant of the Jacobian becomes what? This is also a similar type of question. Singularities occur when the determinant of the Jacobian becomes 0, and then you have infinite end effector, sorry, yeah, then you have infinite joint velocities coming up, which is really not possible. So answer is 0. I hope everything is clear. We already saw this. Okay. A two-link manipulator is shown below and it has two singularities. At what angles? So we already saw this, but just to. What was the Jacobian that we saw? We differentiated it, right? We had L1 cos theta 1 plus L1 cos theta 1 plus theta 2. We differentiated it with respect to theta 1, with respect to theta 2, and then for y also with respect to theta 1, with respect to theta 2, and then we found the answer. I'm solving this question again just to make sure that the concepts sediment. Uh, Please make sure that you understand all of these things. Practice as many times as possible. Differentiating it, writing it, and again calculating the inverse, getting the determinant and everything. This should be well settled and internalized with you. Okay, so please do it. Okay. Minus L1. So this is Jacobian, right? Differentiated quantity. Minus L2 sine 1 to L1 cos theta 1 plus L1 cos theta 1 theta 2 L2 cos theta 1 plus theta 2. ओके, ठीक है. अभी इसका डिटर्मिनेंट we already saw it is L1 L2 sin theta 2. So where is the singularity? When sin theta 2 becomes 0. So your theta 2 is going to be 0 degree or 180 degree and so on. So your correct option is D. Okay, it is clear. Okay, let's move ahead. The minimum energy consumption for the two-link arm given in question 4 is at. So we also solved it, right? We wanted to maximize sine theta 2 and it is 1. So your theta 2 is 90 degree and 270 degrees. We already did this in the beginning. So okay. This is your minimum energy configuration. Okay. The ease of moving in a particular direction.
Excuse me, ma'am.
Yeah.
Yeah, yeah. Could you please previous one slide
Sorry.
show the previous slide, ma'am.
Okay.
On a take screenshot.
I mean, did you understand this? I already explained it. I am not sure if you were there when I explained this.
Yeah, I'm not there, but could you please explain it again?
Sorry.
Could you explain it again, ma'am?
Okay. Yeah, I'll tell you. So yeah, this is the thing that we were discussing. That for minimum energy, when we want to find out what is the minimum energy, we so we have this relation already, right? That joint velocity is related to the end effector velocity in the following way. Joint. Okay, I'll write this also. You know that x dot is equal to Jacobian into theta dot. So from here you can write theta dot is equal to Jacobian inverse into x dot. Okay. For minimization of energy, what do we actually want? We want कि motors के जितनी कम energy dissipate हो. That means we want to lower down the RPM. We want to have as less joint velocity as possible for minimization of the energy. So if you minimize the joint velocity, the only way left with you is you increase the determinant. You maximize the determinant, and then you will automatically experience a change or a drastic fall in the joint velocity, joint energy consumption. All right. So when you try to solve this determinant, your determinant is actually L1 L2 sine theta 2. L1 is a fixed quantity, we cannot change that. L2 is also a fixed quantity, it has a finite value, we cannot change. What we can maximize is sine theta 2. Now the maximum value of sine theta 2 is 1. And when is it achieved? It is at either 90° or 270°. So when you try to write something with your hand, you never place it in a complete stretched position. You do not take it to a completely like contracted position, but you maintain a certain angle. And that certain angle for the minimization of energy is approximately 90 or 270°. All right, that is why we had the answer there. Okay. Yeah, the ease of moving in a particular direction is called manipulation ability or manipulability. For a 2-hour planar manipulator, as shown in question 4, the manipulation ability is equal to what? Okay. So, I told you what is manipulation ability. Just copy that. This is very important. What happened? क्यों copy हुआ? Just a second. Just copy it again. Okay. So for non-redundant manipulators, your manipulability is given by W is equal to determinant of J. So for 2-hour manipulator, that we had, the determinant, you remember, I think now it is settled in your mind that you are supposed to differentiate the x, and so you had an expression for x is equal to function of theta 1 and theta dot, and then y is equal to some function of theta 1 and theta dot, and then you differentiated it with partially differentiated it with respect to theta 1 and theta dot. You got a matrix, and that matrix is called Jacobian. And then to take out the manipulability, we need to find a determinant, and the determinant of J is L1 L2 sine theta 2.
L2 sin theta 2.
Yeah, very good. L1 L2 sine theta 2. Let's say, oh yeah, it is given in the question. L1 and L2 both are 1 already. Then the determinant of J is sine theta 2. So the manipulation ability is equal to sine theta 2. Okay. Okay. After this, yeah, you already saw the ellipsoid, right? What inference could you make from ellipsoid? Let's say my ellipsoid is of somewhat of this kind, and on this axis I have sigma 1, on this axis I have singular value sigma 2. Then what can you infer from this ellipsoid? So this is your major axis of the ellipse. This is your minor axis. So what you can infer from this figure, think about it geometrically. You see the ellipsoid? Here the major axis has a long stretch and the minor axis has a short stretch. So what can you infer? I mean, अगर यहाँ पर end effector है of a robot, let's say here is the end effector of a robot. What would you be able to say about the end effector if you are given this ellipsoid? Anyone? Come on, it was already taught to you. Yeah, Bidu?
And the Jacobian matrix might not be a square matrix.
Okay, that's fine. That's the correct inference that you have given. It might not be a square matrix because you are not able to move equally in all the directions. So you might have
Yeah.
achieved the redundant situation. Any other? Okay, that's true. What you said is true. And apart from that, I would just explain the same thing by saying that your end effector can move only to very less extent in this direction, and it can move to a greater extent in this direction. I mean, for the singular value of sigma 1, you will be able to move certainly in that direction. You will be able to maintain a velocity in that direction, but it won't be possible to that extent in this direction. Okay, I'll take an example. uh, uh, for example, okay, 2R manipulator is the best example for anything, and it is really simple. Let's say this link is L1, this link is L2, this is your theta 1, theta 2 is 0 here, okay, because it is in line. So theta 2 is 0. And then you have a workspace definitely, so it would be somewhat like this. Now, you have achieved this configuration where theta 2 is equal to 0. Okay, so you have achieved singular value. Why singular configuration? Why singular configuration? Because if you are in this position, you cannot move in this direction. You cannot take it forward and backward. The only option available with you is you can move in this direction by maintaining the same configuration. If your theta 2 is 0, let any value of theta 1 be there. You can only move in this direction and you cannot move in this direction. And this is a planar manipulator, right? So you don't have anything to be done in the z axis. Everything has to happen in x and y axis only. So you can only move in this direction. You cannot move in this direction. You have lost 1 degree of freedom by achieving this singular configuration. And then what happens with you is your ellipsoid. So let's say you were in this configuration sometime back. Okay, somewhere here. This was your end effector. You had the complete freedom of moving in a circle. To the extent you could move in this direction, sigma 1, you could also move in this direction, sigma 2. You had the full flexibility to move. You are not constrained that no, you cannot move in this direction. So as long as you were in the central workspace, you had sigma 1 is equal to sigma 2, and it was equal to, let's say if you normalize, then it is 1. So you had equal opportunity to move both of them. So I won't write 1, let it just be sigma 1 is equal to sigma 2. So you had the opportunity to move in both the directions with equal capability. But when you reach here, You cannot really move in both the directions. You have constrained yourself from moving in this direction because your theta 2 is 0, and you can only move along this. If you can only move along this, your ellipsoid gets converted to a straight line. You have no movement in this direction, you just have a movement in this direction. This is your measure axis. Now अभी ये मेजर एक्सिस जो ये वही मेजर एक्सिस है, ठीक है. यू हैव अ मेजर एक्सिस ऑलरेडी देयर, बट यू डोंट हैव एनी वैल्यू ऑफ सिग्मा 2. You cannot move anywhere else. You can just move along this line. All right. So the major axis of the velocity ellipsoid or manipulability ellipsoid is given by largest singular value. So the major axis जो तुम्हारा sigma 1 है is given by the largest singular value in which you'll be able to move. If there is no manipulability in the other directions, it can be like n-dimensional space, right? I'm talking about a straight line, then it is a circle, then it is sphere, and then you have n-dimensional shape. But you will be able to move in that direction only where your system allows. So the singular value so the major axis is given by largest singular value. I hope it is clear. Okay. Now, yeah, this is a question from the lecture directly. So I would just tell you, I think you might have watched the lecture and I'll tell you the answer. The singular value of a non-square matrix are what? What is the singular value of a non-square matrix? I mean, you already saw, right?
Square root of non-zero eigenvalues of A transpose.
Right, right. Very good. So say, if it is a non-square matrix, we want to make it square always. And then we want to, okay. So determinant of a matrix A is given by multiplication of eigenvalues. Let's say if there are two eigenvalues, if it is a second order system, there are two eigenvalues, right? So it is given by the multiplication of it. But since your matrix is non-square matrix, we will have to multiply both of them and then take the eigenvalues from there, find the square root, and then we get what is the singular value. All right. Okay. The last question is the rank of a non-square matrix A is defined as. How is the rank defined? Let's say we want to find out what sigma matrix is from singular value decomposition. Okay, your matrix is sigma 1, sigma 2, and then let's say then you have 0, so it is reduced rank. Okay, so the number of the number of non-singular values that you have actually define the rank of non-square matrix A. All right, that you have understood from SVD and it should be clear. Okay, now we'll do some MATLAB work. So,
Excuse me, ma'am.
yeah.
Ma'am, in the previous question of that ellipsoid, if the Jacobian matrix is given, how can we find out the major axis? Since it is non-square matrix, the major axis is given by the square root of determinant of J transpose. Is it correct? Will be correct, ma'am.
I did not get your question. Just
my question is that the ellipsoid is given, velocity ellipsoid is given, and if we want to find out the major axis, provided the Jacobian matrix is given.
Your Jacobian matrix is already given to you, and from there you want to find out
the major axis.
Okay.
So how will we find it out? So since it is ellipsoid, we can infer that it is a non-square matrix, and therefore the major But how to find out the major axis?
For finding out the major axis, no, you'll have to do this.
Hmm.
Uh, U sigma B transpose. Find this. So
Okay. So
both
that
of
is singular value decomposition.
right. So this is orthogonal matrix. This is orthogonal matrix. This is directly found out from the eigenvalues. So eigenvalues of the matrix A arranged in a diagonal manner
Okay.
in and in a way that it ranges from largest value to the smallest value. So everything that you'll have there, no, will be like if you have sigma 1, sigma 2, sigma 3, sigma 4, this will be the largest value, and this is your largest value, and it is going to be your major axis. Okay.
Ma'am, that we are doing is the singular value decomposition of J or J inverse. J, na?
Yeah, it is J. I mean, you can do it for any matrix. For any matrix, you'll have to do it.
Okay, my doubt came because in the option it is given the major axis of a velocity ellipsoid is found by option is singular value decomposition of J inverse, singular value decomposition of J. Then the third option is determinant of J, and the fourth option is square root of determinant of J, J transpose.
Okay.
So that's why the doubt came. Both SVD of both J and J inverse is given.
Mm-hmm.
And the other two options are determinant of J and square root of determinant of J, J transpose. That is, it is a non-square matrix.
Yeah, it is a non-square matrix. Do you have any other information that if it is uh, a redundant system or any other system?
Nothing is given, ma'am. The question is major axis of a velocity ellipsoid is found by
Okay.
um, J
Okay.
is the Jacobian matrix. Only that information is provided. But from this, nothing redundancy, nothing is given.
Okay. SVD is important, that is for sure. Mm, because we want to find out what are the singular values, and the singular values have to be taken out. So you'll have the singularity problem when you are dealing with J inverse, right? When you for J matrix, you won't be doing it. It will be for J inverse only. I think J inverse option should be correct.
Yes, ma'am.
Yeah.
For J, no need of finding out the SVD.
No, I think for J inverse you'll have to find out. I
Okay.
think I'll look into that once more. So when is your deadline?
Deadline is 19th, ma'am. 19th Feb.
19th Feb. Okay. Uh,
Ma'am, one more question is also there. We have discussed before, like how to find out the torque. And
hmm.
the force is given. A matrix, a raw matrix is given for force,
Hmm.
which is acting on a two-link manipulator.
Hmm.
And we have to find out the torque acting on joint 2. So,
Okay.
like these questions, given L2 is equal to 1.
Okay. So you can use the Jacobian, na?
Okay, so torque is equal to J into F.
Yeah. You can directly use it.
J, J transpose into F.
Hmm.
Okay, okay.
There is another way of dealing with it. I think it was covered in the lecture. Where you have the force, what is the type of manipulator that you're talking about? 2 or 3 r?
A tooling manipulator.
Okay.
Tooling manipulator, ma'am.
Okay. So let's say you have a two link manipulator and then you have the force acting on the end effector. From there, you can
Yeah.
calculate the force and moments. You can take it to the first link and then find the torque. That is also one of the ways in which you can solve, apart from Jacobian.
Okay. Okay. The question is to find out the torque acting on joint 2.
Yeah, I think you'll be able to do it using that method. Why I'm saying this is because this is a method that was covered in the lecture. Okay.
Yes, ma'am. It was
Yeah.
there.
Yeah, when you had the static force acting and then you find out the moments, you translate it to the joint you want, and there you can calculate the torque from
Okay.
the moment equation.
Okay. Okay.
Yeah, you can try that method. I don't know. I
Okay,
think
ma'am.
you should
Okay.
verify it using the Jacobian also. I want you to verify using both. If you are getting the
Okay.
same answer, because Jacobian really gives you an easy way. So if you're going to do that, you'll be doing various number of transformations and then finding out the answer. But in this case, I think the answer would be very direct and you'll get it. So try that also.
Okay. Ma'am, for using Jacobian, we require the angles value of theta 1 and theta 2.
You know, it has to be calculated in the symbolic form only, na? Theta 1 and theta 2. Value is not given, right?
Fine.
So calculated in the form
Not
of
good.
sine and cos only.
Okay.
I think the options would be also in that way only. Sine theta 1, cos theta 1
No,
type of.
no, no, ma'am. Options are same as like non like raw matrix, like 0, 0, 1, 0, 1, 1, like that. Options are
Then you
given like
might
this.
have the things, all of the things cancelling out. It could be one of the reasons.
Okay. Okay.
Try to
Okay.
solve,
Okay.
maybe the terms would cancel out. That is why they have given that way. Else
Okay.
it,
Okay.
else it should have been in symbolic form. Anytime you do it, you will have a sine and cos term always there with L1 and L2.
Cost. Okay. Okay.
And
I'll
maybe
try, ma'am.
if you take the force, take fx and fy, and then proceed forward. Then you'll have the torque represented in the form of as a function of theta 1, theta 2, and fx, fy. All of them would be there.
Okay.
Okay. We'll consider the following problem statement where you have a 2R manipulator with two revolute joints and the link lengths are given as L1 and L2. We'll take some arbitrary values of L1 and L2. And then we want to derive the Jacobian matrix for the manipulator. In MATLAB, you won't be deriving it by doing partial differentiation. Rather, we will be using a symbolic toolbox, SIMS toolbox. SIMS toolbox actually helps you in defining a variable as a symbol. And so the thing with MATLAB is that whenever you define a variable, now you have to assign a value. You cannot directly use the variable everywhere and get the and manipulate and get the answer in the form of variables. You won't be able to do that. If you want to do that, you're supposed to use sims toolbox. Sims toolbox actually helps you in defining all the variables, getting the values or the answer also in symbolic form. Okay, because it is not string anyway, right? It is some variable only and you want the manipulation of those variables without putting in any values. So for that, now the Jacobian matrix of the manipulator is the thing we want to find out. Second thing is that we want to find the Jacobian at a given configuration. So let's say I say theta 1 to be pi by 2, theta 2 to be some value. I want to check that. And then from the determinant of Jacobian, I also want to determine what is, if it is singular, if it is non-singular. So if you're supposed to write a program, MATLAB code for this, how you would write. Okay, so that is the thing we'll be seeing. Second, I'll present my screen also. MATLAB. Where is, yeah, I hope you are able to see my screen. Okay. So our question was, we want to derive the Jacobian matrix for 2R manipulator. Then we want to compute the Jacobian matrix for some particular configuration. And then we want to find out if the uh, from seeing the determinant, we want to determine if this is a singular configuration or this is not a singular configuration. That is all we want to do. Okay. Now see what we'll do. I already just I just want to know how many of you are familiar with MATLAB. I just want to know the audience. You can answer in chat box also, but tell me if it is beginner level or you are familiar or you are not at all familiar. Let me know. Okay. 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 I just mentioned in the beginning that if you're not familiar with MATLAB, use an online version or you can use the open source software Octave. Both of them will really help you. Okay, you're also not familiar. Okay. Actually, yeah, I think you should start practicing. It is very important. I mean, for robotics, you either use Python or you use MATLAB. Familiarization with one of the languages also work, but MATLAB would be good and simple for robotics. So I think you should start with that. I'm introducing you to MATLAB. Maybe you can learn Python on your own. But yeah, do practice these. Okay, let's move on. So the first thing that we'll define is to clear everything from the screen. That is really important. What happened? I think my MATLAB has crashed. Yeah. Close all to close any plot or anything if it is already open. And then we'll use a symbolic toolbox. So I'll comment out the things also so that it will be helpful for you. Uh, Symbolic representation, and what is that is given by Sims toolbox. Sorry, Sims. It is. Let's say we'll have angles, right? Theta 1, theta 2, L1, L2. Okay. Okay. I'll also have real. I'll tell you why sometime later. Symbolic. Okay. Now I'll define forward kinematics for 2R manipulator, because that is what we already know, right? We can directly plug in here. So what is x? X is given by L1 cos theta 1, right? L1 into cos of theta 1 plus, try programming with me. Don't leave it that you'll see that sometime later. It will be good for you. And try to understand the things as well. Theta 1 plus theta 2. This is really simple, right? You can also imagine it that how this thing is coming. Okay. After this, y is equal to L1 into sine of theta 1 plus, correct me if I am going wrong anywhere, into, I'll copy this. Okay. Now we'll compute the Jacobian matrix. And how it is done? So we have already a function called Jacobian. Okay, so I'll use that directly. I'll not be defining the partial difference, like partial derivatives that I'll create a matrix and then I'll differentiate. I won't be doing that. I already have a Jacobian command. So you have to always use this. Okay, so this Jacobian, and how do you enter the arguments here are like this. You write what is the thing you want to differentiate. So it is x comma y, right? Then you put a comma, get the square brackets again, and then you write what is the value using which you want to differentiate, with which you want to differentiate. So that is theta 1 and theta 2, right? So from here you directly get a Jacobian matrix. We won't do anything else. We'll just display it. No, I won't put display. And this would be displayed in Jacobian, would be displayed in symbolic form. It won't be like, since we have not put any values for theta 1, theta 2, L1, L2, it would just display the Jacobian in symbolic form. So I'll write display Jacobian and I'll write, now I want to display the symbolic representation, so it will display J. Okay. I told you to terminate everything with a semicolon. If you don't, you will have everything being printed. Okay. Now I'll define the values. So since I have already used L1 as symbolic, I'll not use that again. I'll write L1 val for taking the value. And let's say I take it to be 1. Okay. L2 val, I also take it to be 1. And then let's say for now I take it to be pi by 4. Okay. After defining these values, I want to substitute it in the Jacobian. All right. So I want to substitute the numerical values. So I'll write J numerical is equal to what were the values. Substitute. In what we want to substitute? We want to substitute it in J. It's going to be J. And then we'll have what we want to actually substitute. In the first row, we want to substitute L1, L2, and then theta 1. Sorry. theta 1 and theta 2. So these are the values which we want to substitute. And we want to substitute with what? So it is going to be L1 val comma L2 val comma theta 1 comma theta 2 value. Okay, so this is the way in which you're substituting all the values. We've terminated with semicolon. Okay, once you have this written, I guess it would come in a lot of, like, you'll have many places after decimal, so I'll just convert it into a double format. So we don't want, we just want 2 decimal places. So I'll write jnum. How do we convert? We can use double function, double jnum. Okay, okay. After doing this, now we want to print the Jacobian matrix with all the values plugged in. Okay, so I'll write numerically substituted Jacobian matrix is. Okay, then I'll write display uh, jnum had the value, right? Yeah. Okay, so we have calculated the Jacobian also. Okay, now after this, what is the thing that is left? I think we should check this, right? Since we have already done this work where we have calculated the Jacobian in the symbolic form, and then we have substituted. So let's see the value. Yeah. So can you like match it from what we had obtained? It is the same thing, right? The first term is minus L2 sine theta 1 plus theta 2 minus L1 sine theta 1. Second term, third term, fourth term, all of them are same. And then in that we have plugged the values L1 val, L2 val, theta 1 val and theta 2 val. So this is the Jacobian matrix that we have obtained. So we really did not calculate anything. We just use the functions to derive all of this. Now let's move forward. We want to check the singularity also. Okay. Okay, so you know that how will you check the singularity? You'll just take the determinant and check if it is equal to 0 or not. So let's do that. So this is going to be compute determinant for singularity. Okay, so we'll be doing this. So can anyone tell me what is the function that is used for getting the determinant? Any idea? How do we calculate the determinant in MATLAB? Is there a function? No idea? Okay, it's just DET, det. You have to write det of, let's say we want to calculate for jnum only. Why should we calculate it for j? We'll have to substitute again. So let's not substitute again. Let's calculate for jnum because we already have it here. Okay. So you get the determinant of j to be determinant of jnum. Okay. After this, we'll display determinant of J is display will so it is already taken to double, right? So we just need to display it. Det J. So you'll get the determinant also from here. Okay. After getting the determinant, we'll check for singularity. So this is the last thing that we are going to do. We'll check for singularity. Okay. When you check for singularity, what we'll do is, if let's say we definitely want to check that it is equal to 0 or not, but let's say it gets some error in double format. So let's keep a threshold value, so that if it is closer to let's say e to the power minus 6, I assume it to be 0. So that way you can do. You can also do it with less, less number of precision values, but for safety I'm keeping it to be 10 to the power minus 6. Okay, so I'll find if absolute of determinant of J, okay, is, if I am wrong anywhere, please tell me. If it is less than e to the power minus 6 or 10 to the power minus 6, I want to display the manipulator is in a singular configuration. Okay. Then if it is not, then I'll use else, and I'll copy the same thing. The manipulator is not in a singular configuration, and then I'll end if else. Okay, let's run it and see what we get. Since the value of theta 1 and theta 2 val are pi by 4 and pi by 6, ideally we should have an answer that the manipulator is not in a singular configuration. Let's check. Yeah, so you see the determinant is equal to 0.5, and then we have it is not in a singular configuration. Now we have another sanity check. What we can do is, let's put theta 2 val to be equal to pi by 2. Why? We talked about our hand now, that for minimizing the energy we took the determinant, and then we said that okay, for L1 and L2 both equal to 1, sine theta 2 should have the maximum value, and then we said that theta 2 should be equal to 90 degree or 270 degrees. Let's see if we are getting that. Yeah, so you get a determinant to be equal to 1. You get a determinant of J to be 1. That means you get sine theta 2 to be 1. And that is the maximum value sine theta 2 can have. And your manipulator is definitely not in a singular configuration, but it is definitely in a mode which is able to minimize the energy consumption. So you are in an optimal mode, operating in an optimal mode. All right. Now, the best check that we want to see is, let's keep the value of theta 1 L1, let L1 be anything, L2 be anything, theta 1 val be anything. Theta 2 val, let's change it to pi or 0. We want to check for both of them, right? Any one of them also works. So let's change it to pi. And what should happen for pi? Your manipulator will be completely stretched, and it should the code should should be able to say that it is in a singular configuration, because you have it completely stretched. Your theta 2 is equal to 0, and it should say that. Yeah, you see the determinant of J is equal to 0 and the manipulator is in a singular configuration. Let's say I'll change the value of L2 to be 0.5. Then also we should have the same value, right? Same answer, right? The manipulator is in a singular configuration, because we already saw that the determinant is L1, L2 sine theta 2. L1 cannot be 0, L2 cannot be 0, sine theta 2 can be only 0, right? And for that, theta has to be pi or 0 in that way. So it really does not matter what is L1, what is L2, what is theta 1. It does not matter at all. What matters is theta 2 value. So I've kept the theta 2 value to be pi and I'm changing L1, L2 values. Let's see what happens. Again, we get the determinant to be 0 and the manipulator is in a singular configuration. Let's say this time I change my theta 1 val to be, let's say I keep it to be 0 degrees. I say that, okay, it is in a horizontal state and then let's see. Yeah, still it is in a singular configuration, right? Let's say my theta 1 val is pi by 4. Again, it is in a singular configuration. So what ultimately matters is what is the value of theta 2. That theta 2 is only the deciding factor for saying that uh, if the manipulator is in a singular configuration or not. So any value that if you have a 0 or pi for the value of theta 2, it is going to decide that. You keep any value of theta 1, you keep any value of L1 and L2, it does not matter at all. Theta 2 also decides how do you consume the least energy. So maximizing theta 2 actually gives you let's you calculate that what is the optimal angle in which my energy consumption should be minimum, and that also comes from there. So given L1, given L2, you decide what is the value of theta 2 and then you get to find, okay, if I have the angle of pi by 2, that is the minimum energy consumption that I have. All right, I hope all of this makes sense today. Um, I want to share this code with you, but I haven't put it in a slide. Put this in the paper that I was sharing, but I'll try to upload this code as well. Before that, I'll just paste the code here. Oh, it was already answered that, yeah, this is the right command. Okay. I'll paste the code here. If you want, you can copy it from here. Okay. Okay, then in the next class also we'll have some questions on redundancy, because that is the topic we'll be continuing with, and we'll have some questions on them. All right. So we are done with the class. Let's meet next Monday at the same time. Thank you.
Thank you, ma'am.